Hello and welcome back to Manifolds. And before we start, I want to thank all the nice people who support this channel on Steady, via PayPal or by other means. Now in today's part 2, we continue talking about the topic of topology. Namely, we introduce notions like interior, closure and related stuff. For this, please recall that a topology on a set X is a collection of subsets that satisfies three rules. First, the smallest and the largest subset have to be involved. Secondly, you cannot leave the topology by finitely many intersections. And thirdly, you also cannot leave it with any unions. So these are the three properties of a topology T, and you also should remember that the elements of T are called open sets. Moreover, the set X together with a chosen topology is called a topological space. Hence, it's a space where the notion of open sets makes sense. Of course, we will also discuss examples of topological spaces here. However, before we do this, we first need more definitions. Indeed, in a topological space, points in X can have special names. Therefore, here let's fix a topological space Xt and a subset S in X. Here please note, S could be an element of the topology, but it does not have to be. Okay, we want to talk about names for points, so let's fix a point P in X. Now, all the names we give for P are to be read with respect to the fixed set S. Therefore, our visualization should look like this. We have the whole space X, and inside we have the subset S. Then, one possibility for P is that P is an element of S. Of course, this alone is not so interesting, but we could have even more. And then we talk of an interior point of S. So what this exactly means, we can now define. Indeed, what we need is an open set, and maybe let's call it U here. Now, this open set should contain the point P, and it should also lie completely inside the set S. And if we have these two properties, we call P an interior point of S. So you see, the crucial thing here is that we find a suitable open set from the topology T. Okay, now it might not surprise you, when we have interior points of S, we also have exterior points of S. Of course, the name already suggests in our picture here, the point P should lie outside of S. However, as before, we want to lie outside even with an open set U. So visually speaking, we want some distance in both cases from the boundary of S. Hence, we need an open set U such that there is no overlap with S. Therefore, this exactly means that P is an interior point of the complement of S. Or with the same formula as before, we find an open set U such that P is an element of U and U is a subset of X without S. Okay, now we have two important terms here, and you see in our picture, we have described all the points inside the set S and all outside of S. Therefore, the points missing are the ones on the boundary of S. For this reason, we could define P to be a boundary point of S if it's neither an interior point nor an exterior point. However, of course, we can also immediately describe this with open sets U. It simply means that no matter which open set U we choose, we always have an overlap with S and the complement of S. Hence, we can write for all open sets U with the property that P is an element of U, we have U intersected with S is non-empty and U intersected with X without S is also non-empty. Then, such a point P with this property we call a boundary point of S. Okay, now you might think that we have all the names, but I still want to include a last one. Indeed, this one is often important when we want to deal with limits, and it's called accumulation point of the set S. And it simply means that the point P is not isolated from the rest of the set S. Hence, as before, we can describe this when we look at all open sets U that contain the point P. And then we want that something from the set S remains. Or in other words, the intersection with the set S should not be the empty set. Here, the crucial thing is that this works no matter which open set U around P we choose. For this reason, you immediately see an exterior point can never be an accumulation point. Okay, so here we have 4 important names for points that are defined with respect to a chosen subset S. Therefore, I would say, please remember them. However, now by having these names for points, we are also able to define names for sets. But don't worry, these are not complicated anymore. For example, for the set S, we can define S circle. This one is simply the collection of all points P in X that fulfill that P is an interior point of S. Therefore, S circle is called the interior of S. So the interior is defined for a subset and it gives us a new subset. And now it might not surprise you that we can do a similar thing for all the other points here. Hence, the next thing will be the exterior of S. However, there we don't have a special symbol, we just write ext of S. Then we collect all the exterior points of S and call this set the exterior of S. Okay, the next important subset will be the boundary of S. Indeed, this one is denoted with a curved lowercase d. It's the same symbol we would also use for partial derivatives. However, here ds denotes a whole set, namely the one with all the boundary points of S. And not so surprising, this one is called the boundary of S. Hence, only one set remains, the one about the accumulation points. And for this one, we have a rather strange notation, we call it S prime. Therefore, for a set, the line in the upper index means that we have all the accumulation points in a set. In fact, one often calls this the derivative of the set S. Another term we will use here is that this is the derived set of S. Now, I would say what you should see here is that we have a lot of labels you should know when doing topology. Actually, there are even more than just the 4 I showed you here, and the last one I really need to show you now. It's an important one, it's called the closure of S. And you see, it has a nice notation, we just overline the set. Now, the definition is not so complicated, we just take the original set S and then take the union with the boundary. And then the set is what we call the closure of S. So, I already told you, this is the last definition I want to show you today. At this point, I really think it's helpful to look at an example. So let's take an example of a topology which is not so common. However, the set X can be very common, so let's take the real number line. On the other hand, T should not be the standard topology, so let's define it in the following way. First, we already know the empty set and the real number line should be included in the topology. However, all the other open sets should be half-bounded intervals. Therefore, each non-trivial open set is such an interval that starts with a real number a and goes to infinity. Here, please note, it's important that the left boundary a here is not included in the interval. Now, it's a good exercise for you to check that all the 3 rules of a topology are fulfilled here. Then, with this knowledge, we can take a subset S and look at the sets we defined above. In fact, the subset S I have in mind is the interval 0 to 1. Also here, 0 and 1 are not included in the set. Now, the first thing we can note here is that this set is not open. So maybe you find it strange to say this, but you immediately see this set is not included in our collection of open sets. It's simply not such an interval here. Therefore, the next thing we can see here is that S has no interior points at all. This is simply because we don't find any non-empty open subset that lies inside the set S. Here, please recall, we need at least one such U with this property to have interior points. In other words, we can't fit an unbounded interval into this interval here. And therefore, the interior of S is the empty set. Okay, now you might ask, what can we say about the exterior points? And there we have to look at x without s. So the complement of s, which is simply the interval from -infinity to 0 and then the union of the interval from 1 to infinity. So there you see, this is better. For this set we find open sets that are contained in this one. More concretely, this works for all points except one here in the second part. Therefore, the exterior of S is simply the interval from 1 to infinity. Okay, now with the knowledge of these two sets, we immediately know all the boundary points of S. There, please recall, these are all the points in X that are neither in the interior of S nor in the exterior of S. Hence, it's the interval from -infinity to 1, including the point 1. Again, this might look strange, but it is simply because our topology is chosen in this way. All open sets stretch from one point to +infinity, so they can't see what happens in the other direction to -infinity. And therefore, we have the conclusion that the boundary of this set is everything on the left-hand side. Okay, and in order to close this example here now, we can also say that the closure of S is exactly the same set. So you see, this here is a nice example in order to get used to topologies. And please never forget, all the notions we have here always depend on the chosen topology. Then I would say, let's go deeper into the field with the next videos. Therefore, I hope I see you there and have a nice day. Bye.